Hello everyone and welcome to today's webinar where we will discuss using Tracerco's subsea CT scanning technology in flow assurance and also integrity applications. My name is Rob Hardy, I'm the Commercial Manager for Europe, Middle East and Africa, and I'll cover the integrity part of the Jim Bramlett in our Houston office to cover the flow assurance part. We're aiming for the presentation to last around 30 to 40 minutes. We'll then leave some time at the end for some questions. So if you do have any questions as we go through the presentation, please type them into the Q&A chat box and we'll run through them all at the end. So just to give you an overview of what we'll talk about today, I'll go into a bit of Tracerco's background. We're going to be focused on the Discovery CT scanner subsea tool today. So I'll talk a little bit about the subsea CT technology. We'll then look at some case studies and real-world examples, starting with complex and coated pipelines. We'll then have a look at internal and external corrosion. We're always interested in pushing the boundaries of the technology and new developments, so we'll look at some recent advances in CT scanning. We have some examples of overstress and fatigue as well. I'll then head over to Jim, who's going to talk about flow assurance, and we should have plenty of time at the end for questions and a general discussion. So for those of you that aren't familiar with Tracerco, I would summarize us as a leading industrial technology company involved in creating unique and specialized measurement techniques. These techniques are used by our customers in detection applications, diagnosis of process problems, as well as measurement of difficult to obtain data and parameters. All of this is geared towards providing our clients with insight and high quality data, which allows them to make decisions on operations and improve processes. As a business, we work in many sections of the energy and chemical process industries, but in this presentation, we're going to focus on our subsea technologies. So this slide summarizes our subsea portfolio of services. FMI was one of the first subsea services we offered and continues to be something we offer around the world. This uses a source and a detector for screening of jacketed structures for water ingress. We've also been involved in grout monitoring at installation of jackets, and this of course is becoming an area of interest in the burgeoning offshore wind sector as well. We also use subsea neutron backscatter techniques for inspection of structures such as midwater arches and buoyancy tanks. Moving on to look at pipelines, we do a lot of work with pig tracking using small source tags on pigs and our gamma track devices, which can be placed at strategic positions on pipelines to monitor the position, the passing of pigs. But we do also, if pigs haven't been tagged at the start, we can use our Explorer technology to scan pipelines and look for lost pigs, as well as look for blockages in pipelines as well. Explorer is quite useful technology to tie in with Discovery as well, because we can use it to quickly screen large areas of pipeline. We can locate lost pigs, but we can also find areas of blockages to then go on and scan in more detail with Discovery. So the Discovery CT scanner is going to be what we focus on the presentations today. So we'll have a look at the technology behind that. One of the main advantages of this technology is that it's a truly non-invasive technique. So it's very similar to medical computer tomography, which is a very powerful imaging and diagnosis technique. So when we take this into the subsea realm, the advantages are that we don't need to remove any coating. We can scan through coating. We don't damage coating that we do scan through. There's no need to remove any coating. You don't need to stop the process at all. So it's a very quick way of getting very detailed information. We collect both the integrity and the flow assurance data at the same time, and we'll see examples in the presentation today how we can change the relative density scale on results in order to look at the same within a pipeline system. We also get real-time data, which we'll see in the fast screening example later on. These are the current specifications on depth, resolution, pipe diameters, but please let us know if you have any other requirements, because we always want to develop the technology and be client-driven in how we develop it as well. This is a short video of Discovery approaching a pipeline. So Discovery is deployed to the seabed in a basket. A work-class ROV then hot stabs in and delivers the tool onto the pipeline. We do take a range of adapters on each project, so that allows us to switch between pipeline diameters as we need to. We use the ROV for power, hydraulics and communications, and we do get real-time data transmission to the service as well. So why do clients use Discovery? Well, it offers significant cost savings on subsea pipeline inspections. When you take into account that you don't have to remove the coatings, you can quickly scan and provide highly detailed data to inform decisions very quickly. There's no interruption to the process, which means no loss of revenue, as well as reducing the overall time from a problem arising to resolving that problem. And subsea CT scanning now gives you highly detailed data on complex pipeline systems. We can build the tomograms that you see on the right-hand side of the image, which give you real insight into what's going on within the system. So moving on to look at some real-world examples. This is a 16-inch concrete coated pipeline. And in this instance, the client didn't want to remove the coating before the scan. This is not a problem with Discovery, and it also means we can rapidly scan and get the data really quickly. The cross-section image on the left-hand side shows how the pipeline looks, and we can see that there's 63 mil of concrete coating followed by a 5 mil polyurethane anti-corrosion layer under this. Below that we can see the pipe wall itself. And then the cross-section on the right is the actual tomogram that we obtained with Discovery. You can see that once the density scale is added, the colours and the interpretation of the data become very intuitive, and it's easy to visualise what's going on. And in many cases you can actually see more detail in the tomogram than the images on the left. You can also see on the image that the steel rebars are visible within the coating. We've also added numerous measurements to the pipeline, so you can start to add the wall thickness measurements and other areas of interest. Below these two images, we've also got a 360-degree wall thickness map of this cross-section. The black dotted line shows the average wall thickness, which was just over 14 mil for this example. The blue continuous line is the Discovery wall thickness data that's obtained. And actually, another interesting feature is the red dots on this line are the UT measurements that the client obtained during the validation of the Discovery tool. And you notice that we get a really good alignment with these measurements as well. In this example, this was a challenge that we had of looking at an unpiggable pipeline that also had a gas piggyback line above it. What we did in this situation was design and construct a custom ROV clamp. This allowed the Discovery to clamp on and scan both pipelines at once. You can see in the right-hand image a photograph of this, the clamp that we produced for this. The tomogram on the left, an example of the data acquired in this project. You can clearly see both pipelines and are able to get the integrity data on both. You can see that wall thickness data has been added and some wall loss defects have been added. It's probably a bit small on the screen, but we've actually labeled 6 different defects on this example. With the Discovery, you also acquire the assurance data at the same time, and the density scales can be changed to look at different substances. What was interesting in this example is that we actually identified a condensate layer that was building up in the gas piggyback line, which could have gone on to cause issues in the future. Again, something unique about this particular example is the way that we scanned it with the clamp. You can see all the nuts and bolts of the clamp that we built as part of this scan as well. This example is a pipe-in-pipe inspection from the Gulf of Mexico. Again, Discovery's unique capability comes into play here as we can produce a very detailed map of both the carrier and the production pipes, as well as both the integrity and flow assurance data. In this example, you can also see the annulus area in some detail. One of the points to note in this area is that there is a faint blue line on the inside of the carrier pipe, which is actually an aerogel layer. And again, you can see in this example, we've been able to add various measurements on different features of the system. Moving on to look at some internal corrosion examples. This was a large diameter gas line. After the scan with the Discovery, we obtained the image on the right-hand side. You can clearly see some instances of severe wall loss around the pipe, most noticeable at the 12 o'clock position. There are instances of broad wall thinning around the pipe, as well as some severe isolated corrosion spots. Also, you can clearly see a section at the bottom of the pipe where a condensate layer is building up, which could be a contributing factor to the corrosion that we see. This was an example where a client wanted to know more about a suspected microbial and bacterial induced corrosion in their flow line. We were able to work with the client and use their own corrosion modelling data and identify hotspots and areas of interest along the line for scanning. The tomogram here is an example of one such area where we identified an area of corrosion. So you can see the area at around about the 6 o'clock position on this scan. Preferential weld corrosion is a threat to most welded joints and something that we commonly look at with discovery. In this example, this was a scan as part of a pipeline lifetime extension project. So what we're doing is going in and we're looking at seam welds to look for evidence and severity of preferential weld corrosion. You can see in the expanded section of this scan, we're able to get these, a lot of detail on this weld. We haven't shown the measurements on this scan, but again, we could look at any particular scan we wanted to and put in measurements there as needed. Discovery is also perfectly suited to scanning both the horizontal and vertical orientations. So this means we can also look at riser integrity. In this scan, we have multiple scans along a riser showing areas differing in condition. The image on the left is what we would determine a good condition area. And then the two images on the right show areas of major wall loss, major corrosion anomalies that were identified during the inspection. In this case, Discovery was used to inspect a known leak within a coated water injection flow line. The client wanted to map and measure the extent of the problem. Visual inspection had identified 2 leaks, but the customer wanted to fully investigate other areas and also guide the repair schedule. So in total, 7 inspection areas were identified. Within these 7 locations, various levels of metal loss defects were identified in all of them. In the 2 locations where the known leaks were, we found the full through-wall defects, and you can see one of these points in the CT image on the right. The image on the left is using the data in a slightly different way to get a 2D representation of the wall plot, similar to how you would see with inline inspection. So the red areas show wall thinning, and the black areas you can see indicate areas of 0 wall thickness. This is the same inspection campaign, and as part of that, we were able to take the data from the 7 locations and build 3D models of each scanning position. So in total, we did a series of 605 scans over a 7-meter section. So this is just another way of using the data to visualize what conditions you have, and particularly useful when you have major defects such as the one seen in this case. So this data was used 1 meter up and down of the defects in order to guide the repair clamp positioning. One of the more recent developments in Discovery is fast screening. So this allows real-time visualization of integrity data when screening sections of interest, and then can go on and inform decisions around more in-depth scanning. A sinogram is produced as the tool scans, which is monitored by our technicians. And as you can see in the 2 images here, we have a lower resolution image on the left. That's produced after 1 lap, and a much higher resolution image after around 20 laps. Although they're clearly differing in the resolution, you can see that the defects showing up in the lower resolution image are already visible. The defects shown in the higher resolution are already visible after 1 lap. So note this is a relatively raw sinogram and different to the density map tomograms that we have already seen. This data is presented for a single 15mm slice, and it's plotted as the rotational position of the source changes. So although it does look like a pipe, it's actually data for a static scan and shows the same defect present as the relative position to the source and detector changes. So the white line that you see tracing through the image is actually the same static defect, and it's actually the source and detector that are changing in relative position as we build up the data. So with this fast screening, you would instantly identify this area as an area of interest with possible defects, and you would want to go on and do a more detailed scan. If you did a fast screening and didn't see any defects, the tool could then simply step onto the next section. So this is an example of a fast screening being used at a customer location. After the standard delivery and clamping on of Discovery, we completed a full scan and data acquisition at the first location. This is acting as a baseline data before we go into the inspection area. You then have an area of fast screening ahead, which can be up to 4 meters long. We're then looking for any variance within the section from the baseline data. So the process then becomes baseline scan, step along, complete a fast scan, monitor the data, decide if you want to complete a full scan or move on to the next. If there's no change from the baseline data, then the tool moves on until the next predetermined area for a full scan. In this case, that was set at every 20 screening scans. If an anomaly is detected in the fast screen, then this triggers a full scan. Again, a recent development that has been used in Discovery is baseline scan on new pipelines. So in this case, we work with the operator to look at their own corrosion modeling data and determine areas within the new pipeline that would be areas of interest. Once the baseline data has been acquired, Discovery will then be deployed annually to monitor corrosion growth rates in these locations. We've got an example tomogram that we obtained here. As we expect, we have consistent wall thickness measurements. However, one thing to note was that the position of the production pipe is not ideal and isn't sitting dead center, so we were able to advise the client on that. Overstress and fatigue can also be identified with Discovery. So in this image on the right, clearly annulus integrity has been lost, which could have been due to the lack of centralization of the production pipe or damage to the centralizers. The thermal expansion has then allowed this to sit right up against the carrier pipe. This could lead to flow assurance issues as well as potential corrosion problems. So Discovery can also be used to check the effectiveness of the thermal expansion design. In this example, Discovery was able to identify some interesting instances of movement and vibration within an interior gas lift riser. So this has the potential to again cause fatigue damage. You can see from the image that this is an example of a pipe within another pipe, with the innermost pipe being the gas lift riser. The middle is the production line and a heavy wall carrier pipe on the outside. Again, another interesting feature here is that there's an umbilical located in the outer annulus as well. If you look closely at the gas lift riser, you can see that the image is jagged and distorted, and this is from movement during the scan. So there's risk of fatigue damage from this movement. Based on these results, we worked with the operator to do some monitoring at that location. The goal of this was to understand the slugging that was happening in the gas lift riser, as this was contributing to the fatigue. So looking at the image above, which is a blue color scheme, this shows the initial data, and you can see that there's short areas of lighter blue before darker, and that's repeated in quick succession. So that's showing slugging passing through in quite a high frequency. The operator was then able to make slight changes in their system, and we then performed a second scan with the results shown below in the yellow color scheme image. In this, you can see the slugs showing up in lower frequency in the longer areas of red. So in this instance, the client has been able to reduce slugging frequency and take some of the stress off the gas lift riser. Okay, I'll now hand over to Jim Bramlett, who's going to take you through the flow assurance slides.
Great, thanks for that, Rob. I appreciate that. So again, just to kind of touch a little bit before we go all through the flow assurance on to build a little bit on what Rob was saying. So one of the key benefits of the technology that we're discussing as far as Discovery is concerned is the unique ability of the tool to do both flow assurance as well as asset integrity, and it's all within the same scan. So in other words, we don't have to go out and change what we do to gather either flow assurance data or gather inspection data. It's all done all at the same time. So even if we are on a primary asset integrity project, we obtain the flow assurance data as well. So we provide a health check, so to speak, on all the locations that we have taken the integrity data. Vice versa, if we're on a primarily focused flow assurance project, we are also obtaining that inspection data as well, and we report that as a health check, so to speak, for the integrity side of things. So why is flow assurance important to us? You know, research has indicated as we started down this path that 50 to 80% of remediation attempts fail on the first attempt. Now, why do they fail? It's not because something went drastically wrong. It's that you can only base your decisions off the data that you have available to you. And what our tool does is the ability to confirm or change your view on what is actually the problem, and that has a chain fall effect on how you actually approach the remediation, the size of vessels, the attempts that you make, whether it's a chemical, mechanical, whatever the function is, right? So that's kind of where we've come in with the flow assurance aspect. So if we look at flow assurance, next slide, Rob. There's 4 steps to a cost-effective remediation. The first is you've got to know exactly where the problem is. And we use 2 functions. One is our Explorer technology, and I'll do a brief overview of that just so you get a feel for it. Or we can also do that with Discovery. Explorer just allows us to do a large section of pipe relatively quickly and look for the anomalies. So where do we need to go? The second is to know exactly what it is. So what am I up against? How much of it is there? And what does the structure of it look like? To give you some examples, and we'll look at a few of them. Is it a solid bore blockage, or is it a partial blockage? So in other words, can I get a contact chemical to it, or am I going to have to mechanically remediate? From a hydrate, is it multiple hydrates or a single hydrate? Is it a long line of what we call snowy hydrate, and you'll see an example of that, or is it a solid block ice hydrates? Those. Obviously, the third is to effectively remediate it in a cost-effective manner, and that's by knowing what you have and heading out on the very first attempt and knocking that problem out. And then the fourth is you can use Discovery to monitor the effectiveness of that remediation campaign, because one of the questions always is, how long is it going to take? We can actually start monitoring that remediation attempt and look for the disassociation or the chemical cleaning, whatever it is, to look at how much progress is being made over time. So therefore we can extrapolate exactly about when we expect the remediation to be complete. Next slide, please. So real quick, a little bit about Explorer. Rob talked about the technical aspects of Discovery. So Explorer works in a little bit different way. It's much smaller, be stabbed in the mud, it can do long runs of pipe, and all it does is it's taking a average of the cross-sectional density of the pipe. So without being able to go in and pinpoint every location within the production pipe, we take an average cross-sectional density, and from there we can look at differences in the density profile throughout the pipeline, i.e. look for those anomalies. And a couple examples I'll show on the next slide. So this is imperative or indicative of information that we would get from Explorer. So real quick, I'll kind of explain what we're looking at here. If we look at the bottom axis, all that is distance from a known point, right? So we've started at point A, we've ended at point B, and these are the distances between those points, and we take measurements with that. The axis to the left will be density, that's in grams per cc. And then the axis on the right will be depth, right? So we can monitor our depth ratio. And what we're looking at here is we're looking at an area of interest of high density. So what we have is where the circle is, that's a hydrate front side, back side with liquids trapped in between in a gas line. And we take these readings, we take 2 readings at each location, the 3 and the 9 o'clock position and the 12 and the 6 o'clock position, and we overlay them. We want to see them overlay extremely well, which pinpoints that the data is accurate. We're not looking at a potential light layer of sand that elevates our overall density. And again, the reason being is this particular tool just gives a average cross-sectional density between source and detector. But here we've clearly identified one area of hydrate instance. Next slide. As we work further down the line, you can see that we jumped up into another high dense area where we've identified anomaly, and then continuing to go past that, we've got just a mixed mosh of high density material. Next slide. And then finally, we can see here where we have a distinct density differential where we drop back down into fluids from hydrate, and then that runs on past this and drops back into gas. So with this, we've got a clear understanding of where issues are. Now we can use Discovery to go back in and clarify exactly what it is, what the extent of it is, and what the structure of it looks like. Next slide, please. So from a flow assurance standpoint, you've seen some images like this from the integrity side. However, here we've now focused on the production. So the only difference in the data that you see between integrity and flow assurance is just that one, we're focused on the pipeline or the pipe wall itself. For flow assurance, we're really focusing in on densities that are much tighter, much lighter, and within the production pipe. So all we do in layman's terms, if you think about a camera, if I'm trying to focus on something 6 inches in front of me, but I'm also trying to focus on something 200 yards out, it becomes very difficult. So I need to just focus on one or the other. And that's all we're doing with the data when we switch between looking at the pipe wall integrity as well as the flow assurance. And these are just a couple of quick examples of different flow assurance issues that we have found, so you get a visual representation of it. And the first pipe and pipe on the left, that's a clean pipe, it's good production, everything looks beautiful. If you switch over and you look at the image on the right, we have a definite structure buildup in there based on the densities of 1.2 grams per cc. We've identified that as an asphaltene. And it's a more of a tarry liquid type asphaltene that's able to hold some structure. And then you've got a gas, bore channel up at the very top. Next slide, please. Here's two different ones. Here's a different asphaltene. It's a much drier asphaltene in the image on the left, where it's holding structure, but it's got a lot of trapped gas in it, right? So we call that kind of a honeycomb effect type. What we're able to do is we're able to go in now and look at the image on the right and identify whether that's a bore channel that's all the way through or whether that's just a trapped gas pocket, because that becomes critical if you're trying to get a contact chemical in order to remediate that asphaltene. The image on the right is a pipe and pipe with a scale buildup. So it's much higher densities. You're in the 2.3 gram per cc. So we know that's in the scale density range. It's much too high for any wax or asphaltene or hydrate. And we get a clear indication of that buildup. And then obviously the operator at that point can make adjustments and do cleaning mechanisms to make sure that doesn't become a full bore issue or reduce your ability to get flow through the pipe. Next image, please. So here's some examples of hydrates. So some different hydrates. We've got an image of on the left of static. Now remember, we're looking at very small density difference. So we've got oil, water, and gas. We can clearly see those three layers in the image on the left. In the image in the middle, if you'll notice, it's very packed. It's a solid chunk ice buildup hydrate with a gas channel on the top. And you can start to see is exactly what we would expect, that the hydrates start to build up as they go up around the pipe wall. And you can see that you're perfectly clear at the 12 o'clock. But if you look at the, let's say 10 and 11 and 2 o'clock position, you can start to see the hydrate build up and grow up along the walls. Whereas the image on the far right is totally different, right? That is a much more what we call snowy hydrate, where you've got crystallines that are growing and bridging across the pipe. The interesting fact with that is that obviously the image on the right will be able to be disassociated much quicker than the image in the middle, and that becomes valuable to the remediation campaign to understand, hey, it's going to take a little bit longer, but we're watching it. We are making progress, and that's one of the key factors. You don't want to sit out with vessels and equipment and all that, thinking you're attacking something for weeks on end and millions of dollars in cost to only come back and figure out finally that you're not making any progress. Next slide, please. So the final opportunity, or the third phase, is to do the effective remediation, right? So know what you have going in and be able to attack it in the right position. So again, if it's a contact chemical, let's say it's an asphaltene, but you've got a solid bore asphaltene, you're not going to get penetration through the chemical. or with the chemical contact chemical, and you go out and do a xylene treatment ahead of time, just hoping it'll work, that's a $10 million shot on the high end, not counting loss of production. When if you would have had the data beforehand, you would have known that if that remediation attempt had no chance to succeed in the first place. So again, it's critical to know all that information beforehand if you want an effective remediation campaign. Next slide. And this just shows the ability of the tool. This happens to be hydrate as well, to be able to watch the disassociation of the hydrate. Now, what you see here is some grainy, much more grainy images. And what that is we are in both the images on the right, or excuse me, the left and the center are in a single location as the hydrate is disassociation. So much like you saw with the pipe and pipe moving, the gas left fiber pipe vibrating. In this particular image, over time, you're seeing the hydrate melt and slough, and it gives us that grainy image. We're able to tell at that point that it's moving or it's changing over the time of the scan, and the remediation is working at that particular point. And then again, the image on the far right just shows the oil, water, and slight ice layer laying in the pipe. Next image. A little case study that we'll go over on one that we did, and you'll see one of these images, the fourth image down, you've seen before previously. This was a line that was quite interesting. It was showing elevated DP as they went into an emergency shutdown, although they had flow. When they did what they had to do on the shutdown, they started production back up. They blocked the pipeline. They immediately thought, based on that they had issues with hydrate buildup. So they just started a hydrate remediation campaign of just drawing down pressure, pressuring back up, drawing down pressure, holding pressure back up. They kept getting slight movements. So they thought that they were actually moving, and they continued that remediation attempt. At some point along there, they couldn't get any more pressure in the pipeline. They couldn't get any more movement. At that point, Discovery was launched. We went out to take a look at it, and it was quite interesting. As soon as, I guess I should back up, as soon as they couldn't get any more pressure, they thought, well, maybe it's not a hydrate. So they dumped xylene in, thinking it was potential asphaltene at that point. And the interesting thing is, this is the actual results. These are just 5 scans periodically along the pipeline for the case study example. If we would go into zone 1, we found the xylene head. We could calculate the amount of xylene that they put in there, matched perfectly. When we entered zone 2, we entered what we called the solvanic asphaltene, where we actually had some transition from full xylene to full bore asphaltene. Zone 3 was solid block of full bore asphaltene. Once we entered zone 4, we entered that what we call that honeycomb look. So we've got that dry, real dry asphaltene with the trapped gas all in between it. And then as we went further down the line, we went into the more tarry like asphaltene that actually sloughed over time as they didn't have production through the pipe. And then that's what you see there. Come to find out, what had actually happened is after the fact, now that we have this data, is they actually had the asphaltene blockage, which looked like zone 4 primarily through. They thought they had, again, they thought they had a hydrate. As they drew down pressure, it accomplished nothing. As they pressured back up and pressure spiked, they packed that asphaltene. So you can imagine with pressure, they just collapsed it. And that ended up causing the zone 3 issue, which meant that the xylene treatment had no chance of getting through because it was full bore block packed asphaltene. And at this particular point, mechanical remediation or a lost line is the only options available. Next slide, please. One more case study to go through and just show you. This was an example of an issue where we had a client that was pretty convinced they had an asphaltene issue in the pipeline. They wanted to bring us out to verify that before they changed and went in with a remediation attempt. And what we found here was the scale issue that you see in the image on the tomogram on the right bottom. So that quickly changed them, right, to determine exactly what was going on within the pipeline, changed their remediation attempt. They went in with scale inhibitors and tried to clean. And what was interesting is we got a great quote from the flow assurance engineer that said that they had learned more in 10 minutes of reviewing scans than they had in 2 years of modeling. And that's not a knock on the models. It's not a knock on the flow assurance engineer. It's just a simple fact that your models are only going to work, or the effectiveness of the models are only going to work based on the quality of the data that you're able to put in. And this gives you the exact information to put in and take a look at your flow assurance issues. So with that, we have any questions?
Yep, thanks, Jim. Yes, I'll keep you in the hot seat for a moment if you like, and we had a few questions come in, so I'll throw them to you.
Sure.
First one, we mentioned about coatings, but what about removal of marine growth?
So typically we don't need any marine growth removed as long as it's not just crazy marine growth, right? Soft marine growth is typically not an issue. If we get a case of severe hard marine growth, that could be an issue. However, typically we're working with this tool mainly at depths that we're not going to run into any of those problems.
Mm-hmm. Yep, thanks. Okay, next one. We covered a few of these examples in the presentation, but if the contents are multi-phase, are there any changes to the scanning protocol at all?
No. So with Discovery, with Explorer, we couldn't do it on multi-phase in production, so to speak. So if the flow line's operating, because we're taking an average cross-sectional density, those numbers are going to change throughout and skew the results. So it has to be a down flow line or a blocked flow line for Explorer to work well. With Discovery, it's irrelevant. It doesn't matter to us whether it's flowing, multi-phase, whatever the situation is. And again, if you revert back to some of those images where we showed things that are changing during the scan versus things that are static during the scan, it actually doesn't affect us at all, for the simple fact that the buildup or blockage is going to be static. We're going to see that. Whatever's flowing, whether it's multi-phase or not, will give us a ghost or shadow effect, and we're still able to distinguish between the buildup and the production.
Great, thanks. How long does a scan take, and can you cover lengths of pipe? Again, I think we covered a few examples, but maybe we'll just cover that again.
Sure. So a typical scan for Discovery, and I'm just going to throw average, it'll obviously depend on the rule or the principles of radiation, right? Time, distance, and shielding. So depending on how much shielding, i.e. Pipe wall thickness, coating thickness, size of overall pipe, production fluids, and so forth. But right now, a typical full Discovery scan on most pipes is running 10 minutes or less. And a quick scan is a minute or two. Or fast screen, excuse me.
Yeah. And then we mentioned a little bit about, so we're doing this in 15mm cross sections, but we can step along the pipeline, can't we, and do multiple scans along certain lengths. Although if we were looking at very long distances of pipeline, we'd probably do initial scans with Explorer to identify areas of interest, and then go into the Discovery scans later on.
Yeah, absolutely. And of course, it's very dependent on what your primary focus is, right? So if your primary focus is integrity, you're typically looking at 100% scan of a known distance, right? So we'll be placed on the pipe at that point. The ROV can let go of us to stay within umbilical reach, and we will scan and walk that tool right down the pipe to the scope of work that's already predetermined as far as distance, right? Typically, if it's flow assurance, we're not focused on every 15 millimeters. We're focused at known distances apart as we build the pipeline up. So at that particular case, it'll probably be scan, then the ROV will move us a certain distance, and then we'll scan again, move, scan. So it depends on the primary focus of the project as to how we set that up and attack it.
Yeah. Great. Okay. Next question was, can this technology be applied to onshore oil pipelines?
In theory, yes, and that's where it all started, right? However, right now we're licensed with Discovery, subsea. We've primary focused with subsea. With Explore, we do this quite regularly downstream on access pipe, where we're looking for buildup in plant pipes and so forth. In theory, we could do the same with Discovery. We would just need a business case to determine that. However, we do have a cruder form of that where it's not quite to the detail of Discovery that we do downstream or onshore, where we can actually do what we call a through pipe scan, where we run similar principles as Discovery, just not to the detail level.
Mm-hmm. Okay, great. We had a question about scanning through concrete coating. Again, that came in quite early. I think we covered a few examples, so we can scan through concrete coating.
Absolutely.
Yeah, anything extra to add on that, Jim? I think.
No, it's just the benefit of being able to scan through the concrete coating, right, without having to do the coating removal, which is extremely time consuming. Is now operators have the ability to, in fact, scan from the external without any risk of production with Discovery and get the integrity data under the concrete.
Mm-hmm. Great. Next question was, what is the data processing time after measurement?
So we get the measurement topside instantaneously, and it takes, depending on how critical it is, it takes our project lead a couple of minutes to look at each scan.
Mm-hmm.
So it can be relatively fast. From a flow assurance standpoint, we want to make sure that we look at that data very, very carefully, because that will or could indicate our next move. Where do we go next? Whether we take a big jump or small jump. From an integrity situation, it's more of just verifying that the data is good and that there's nothing super critical there. If there's something critical, then we will notify the company rep on board to take a look at it. And it's also critical to be able to look at that if we have a defined, let's say, 2-meter scan section that the client wants, and we get to the end of that 2-meter section and we're actually still in the middle of a defect, we have the ability to put that back on the client and say, okay, do you want us to stop here, or do you want us to run that defect out? The benefit of that, obviously, is the last thing you want to do is get back to the beach, demobilize everything, and then all of a sudden wish you had more scans or wish you had something different. We're able to do that real time offshore and make those decisions, saving countless amounts of money at that particular time.
Yeah, okay. Next question was, should the pipe be suspended to be scanned, or is laid on the seabed okay? And we saw in some of the photos and videos that we do need 360-degree access, but yeah, maybe you want to explain that a bit more, Jim.
Sure. So we do need 360-degree access, and the way that we do that now is, again, it kind of goes back to what is the primary focus of the project. Is it flow assurance, where we're going to take big moves, a lot of scans at different locations? It becomes cumbersome at times if we haven't used Explorer to determine exactly where to go. So at that point, it's probably easier to lift the flow line, right? To open up large sections of pipe. If it's integrity, it's typically done with corrosion modeling. We have known locations that we're going to, and at that particular point, you can dredge those locations, and then we'll go into those dredge holes. At that point, put the tool on and scan those particular locations. So again, it just, Rob, it just kind of focuses back on what is the scope of work and the primary focus of the project.
Yeah. Okay, thanks, Jim. Next question was, what kind of coatings can be handled? We did kind of focus on concrete coatings a lot there, but Jim, maybe you can give a bit more of your experience on different coatings and other types of pipelines that we've worked on.
Yeah, you bet. So just to kind of make it easy to understand, as long as it fits in the tool, it's not going to affect us. Okay, so it doesn't matter what the coating is. We can go through that coating and get the pipe. We haven't come across anything that we haven't been able to go through yet. And again, if you can get through that concrete, you can pretty much get through anything else that's out there.
Mm-hmm. Great, thanks. Next question was, how can we tell if there is emulsion occurrence?
It would depend on what the emulsion layer is, right? But if you want, based on density differential, but you know, we've seen the image there where it's clear that we can distinguish the difference between oil, water, and gas. Again, if it's super tight density, it would, or it could become cumbersome to try to identify an emulsion layer. But if there's enough density split, then it's irrelevant to us. We'll be able to see that emulsion layer. If that, hopefully that answers the question.
Yeah, thanks, Jim. Next question, do you need divers to deploy, operate, or buy ROV?
Most of everything that we've done is ROV. There could be a situation, I believe, where divers could be used, or we could work it for a diver operated system. But primarily right now we're doing most of the work, or all the work that we've done to date has been with ROV, I believe. I may be wrong there. Rob, have y'all had any projects with divers?
No, we haven't. Yeah,
typically in the Gulf we've all used ROVs for the application.
Yeah. And there was a question, what class of ROV again? So yeah, it's mainly been a work class ROV that we use.
Yeah, just based on the size of the tool, we're going to need to use that work class ROV to be able to maneuver it. So to give everybody an idea, you're looking at roughly 250 pounds in water with buoyancy.
Yeah. Okay, next question. Can the technology be used for composite pipes and other non-metallic pipes?
It can, but again, it depends on the density, right? So we have looked at different pipes. However, there are some composites that are extremely close to the density of water, and we have to be careful with those. So it would depend on the density differential. Again, that's all we're looking at is density differentials, right? So if there's enough density differential between the composite pipe and the water itself, we can actually see that no problems whatsoever. We're actually in the middle of a trial right now for composite repairs where we can actually see the composite repair. We have identified delamination and air trapped in between, as well as the external pipe wall defects.
Yeah. Okay, that's great. So that covers all the questions that have come in. So we've got our contact details up on the screen. So if anyone wants to email us, get in touch with anything else, feel free to. You can also find us on LinkedIn or just go to the tracerco.com website as well. So unless there's anything else, Jim, I think we'll end the webinar there.
Great. Appreciate it, Rob, and I appreciate everybody's time and attendance.
All right. Thanks, everyone, and talk to you soon. Thank you.